Okay, so this is what I meant just now, the scales, right? For NMR scales, for carbon, they usually start at 0. So the TMS signal is always here at the beginning. So wherever TMS is, that's where 0 is, okay? So the purpose of adding TMS is to tell us where 0 is. So for carbon, right, it generally goes from 0 to about 220, 240 here. And then for hydrogen, it may go up from 0 to about 12, maybe maximum 15 it goes up to. Okay, so the frequency range for hydrogen is smaller. Meanwhile, for carbon, it is bigger. Okay. All right, so we're going to look very quickly at carbon NMR. So if you look at this picture here, okay, look at this picture here. So I want you to notice, right, this molecule, if you want to understand this better, what you can do is you can draw it like this. Okay, so you can let's say we redraw this, right? So there is carbon here, there is hydrogen here, and there is chlorine here, and then there is this CH this side, and then there is CH3, right? So to help you understand this, what you can do is you can imagine each one of this is like a ball. Okay, it's a ball, right? It's a ball. So all of these are circular like a ball. Okay, so now this might help. So if I told you symmetry, what you're going to do is you're going to cut this ball right in the middle here like this. So you will end up getting two halves, right? So that means you get one half here and you get an identical half on the other side, correct? So you can actually get two equal halves. That's what I mean, right? So you can get two equal halves. So here it means that the signal which is produced by this the signal which is produced by this hydrogen, this hydrogen, this hydrogen, this and this and this and this is identical. So which means that on a scale of 0 to let's say 15, okay, this is what we did earlier. So you get one that is like 6, and then there is only one hydrogen here. This is a chlorine. So you get one very small line here. Something like that. So you'll get two signals, only one signal very tall and the other signal very short. Meanwhile, for carbon you only have two signals, right? So there is this carbon A, and then this carbon is also A because they're mirror images, and this carbon is B. So the ratio of the carbons, okay, 0 to let's say 220, 0. So carbon A would be taller and then carbon B would be shorter. Okay, so this is the spectrum. You see here, this is the spectrum. So you notice that this carbon, this is taller, so this would be roughly at about 2, and this is roughly about 1. Okay, and so the other thing I want to tell you at this moment is that this signal is a little bit further away from zero because this carbon is directly bonded to an electronegative element. So when you're bonded to somebody who is electronegative, like chlorine, bromine, oxygen, your signal is usually further away from 0. Okay, further away from 0. That's how it's supposed to be lah. Okay, let's look at another one. So this chemical shift data will be given to you during the assessment. So it helps you to kind of narrow down who is who. So here, look at this molecule here. You will notice that in this carbon NMR, there are only two carbon environments. There's no symmetry. You cannot cut this molecule in any way. So you see one carbon here and you see one carbon. So, and both of them are equal. So the height is the same. And since this carbon is directly bonded to an electronegative element like oxygen, the signal is further away from 0. Okay, further away from 0. Okay, let's look at benzene. Why does benzene only have one signal? And the signal is here around 120, 140. Why only one? So for benzene, right, you can actually cut benzene like this, and you can cut benzene like this, all right? And then you can also cut benzene in this way. You can also cut benzene in this way. That means that's like perfect symmetry. You can cut it any direction. So it basically means that every single carbon in benzene produces the exact same frequency. That is why you see only one signal. Okay, I repeat. So for benzene, you can cut it this way. So one, then you can also cut it this way, and then you can cut it this way, and then you can cut it this way. Whichever way you want to cut it, there is perfect symmetry in all directions. So which means that this carbon, this carbon, this carbon, this carbon, this carbon, this carbon, they all produce the exact same frequency. So this is the spectrum for benzene. Chlorobenzene, on the other hand, Now, if you imagine this to be a ball, you can cut it only this way. Okay, you can cut it this way only, up to down. You cannot cut it this way. This way you cannot cut. So what does this mean? It basically means that this carbon are identical to each other. This carbon and this carbon is identical to each other because they are mirror images of each other. This carbon and this carbon are not the same. Okay, they are not the same. So how many carbon environments do you have? You have 2 purples, 2 reds, 1 pink and 1 yellow. So the ratio will be 2, 2, 1, 1. Okay, so this is how it looks like. See here? So 2, 2, 1, 1. Okay, 2, 2, 1, 1. So sorry. So you see these two are the same height. Alright, they're same height. And then the other one. So this one, right? This carbon, okay, so you see this carbon here, this yellow carbon is connected to chlorine. So since it's connected to chlorine, this is the signal for the carbon which is connected to the chlorine. This signal which is closer to the yellow, closer to chlorine, the purple one, this, I suspect this will be the purple. This is actually the purple. And this will be the next one which was red. Okay, so this will be the red. And the last one which was the furthest away from chlorine and everybody else, pink, would be here. That's the signal. Okay, so that's the pink one. Okay, so let's look at this one. The following is the carbon NMR for 1,4-dimethylbenzene. So 1,4-dimethylbenzene, so benzene is something like this. Okay, it's a hexagon ring. So it has 1 methyl over here and it has 1 methyl over here. So in this case, I hope you realize you can split it this way. You can also split it this way. Alright, so which means that this hydrogen, sorry, this carbon, this carbon, this carbon and this carbon are identical to each other because it's like symmetry in 2 ways, right? You can cut it straight, cut it across. Then this carbon, this change color, this carbon B and this carbon B are identical. And then finally this carbon C and this carbon C here are identical. So this one is the signal which is produced by this carbon, and this signal around 120 to 140 are the carbons in the benzene ring. So this obviously is the A's and this is obviously the B's. So for benzene carbons, right, the signal will appear between 120 to 140. So this is the methyl which is outside of the benzene ring. Okay, so this is carbon NMR. So next we will look at proton NMR, and then after that we'll be done because I need to explain to you the n+1 rule splitting.